The universe is vast. It's filled with wonders we're only just beginning to understand. We see galaxies spinning in the dark, great clouds of gas where new stars are born, and planets orbiting distant suns. These are things we can see, things we can measure. But, what about the things we can't see? What about the places where our laws of physics seem to break down completely? The cosmos holds secrets in its darkest corners, mysteries that challenge the very limits of our imagination. We look up at the night sky, a sea of twinkling lights, and we just can't help but wonder what lies beyond the familiar patterns of the constellations. It's this fundamental human curiosity that drives us to explore, to question, and to seek answers about our place in the grand cosmic scheme of things. Among all the cosmic enigmas, one stands out. It's a place of such extreme gravity that nothing, not even light, can escape its grasp. We call this a black hole. The name itself kind of conjures images of an endless void, a cosmic monster devouring everything that strays too close. For a long time, that was our only picture of them. To understand this extraordinary possibility, we first need to understand what a black hole is. Think of gravity as a fabric, a vast cosmic sheet called spacetime. Massive objects like stars and planets create dips in this fabric. The more massive the object, the deeper the dip. A black hole is what happens when you have an incredible amount of mass packed into an impossibly small space. This creates a dip so deep, so steep, that it becomes a bottomless pit in space-time. This is a point of no return. Once you cross its boundary, known as the event horizon, there is no coming back. In 1963, a New Zealand mathematician named Kerr did something remarkable. He found a new solution to Einstein's equations of general relativity. His solution described a black hole that was rotating. This was a game changer. Unlike the stationary Schwarzschild black hole, the Kerr black hole was a dynamic spinning entity. This rotation fundamentally alters the structure of spacetime around it. It doesn't just create a simple dip in the cosmic fabric. It twists and drags spacetime along with it, kind of like a spinning ball dragging honey around it. This effect is known as frame dragging, and it creates a region outside the event horizon called the Ergosphere. The Ergosphere is a fascinating and bizarre place. Within this region, spacetime itself is spinning so fast that it's impossible to stand still. The most dramatic difference between a simple black hole and a spinning one lies deep within its core. In a non-rotating Schwarzschild black hole, the singularity is a point. All the matter of the collapsed star is crushed into a single, one-dimensional point of infinite density. It is the ultimate dead end. However, in a Kerr black hole, the rotation changes everything. The centrifugal forces from the rapid spin actually prevent the singularity from collapsing to a single point. Instead, the singularity is smeared out into a one-dimensional loop, a shape we call a ring singularity. Think of it like a cosmic smoke ring of infinite density and zero thickness. The influence of a Kerr black hole's spin begins long before you reach the event horizon. The frame-dragging effect creates a unique region of space-time around the black hole known as the Ergosphere. The name actually comes from the Greek word ergon, which means work, because it is, at least in theory, possible to extract energy from this region. The ergosphere is this oblate or flattened spheroidal shape that touches the black hole's event horizon at the poles and extends furthest out at the equator, where the spin is fastest. It's a place where the twisting of spacetime is so extreme that it dictates the rules of motion in a bizarre and inescapable way. Once you enter the ergosphere, you're caught in the grip of the black hole's rotation. Space-time itself is being dragged along faster than the speed of light. Now, this doesn't mean you're traveling faster than light, which is, of course, impossible. So, the strangeness of the Kerr black hole continues as we move deeper inside. A simple, non-rotating Schwarzschild black hole has just one event horizon. This is the single, well-defined boundary that marks the point of no return. Once you cross it, your fate is sealed, and your journey ends at the central point singularity. It's a straightforward, if terrifying, one-way trip, but the spin of a Kerr black hole complicates this structure dramatically. It splits the single event horizon into two separate and distinct horizons. This means a Kerr black hole has an outer event horizon and an inner event horizon. The outer horizon behaves much like the one we're familiar with. So, putting all these pieces together, we can now see the theoretical journey through a Kerr black hole. It's a voyage unlike any other imaginable. You would begin by entering the swirling, chaotic Ergosphere, where space-time itself forces you into a spin. Then, you'd cross the outer event horizon, the first point of no return, sealing you off from your home universe forever. You would find yourself in the strange region between the two horizons, a place where you are trapped, but not yet destroyed, with the pull of gravity still guiding you inexorably inwards towards the next boundary in this cosmic maze. Next, you would approach and cross the inner event horizon. This is the final frontier. According to the pure, idealized mathematical solution, crossing this boundary opens up the path to the central ring singularity. With careful navigation, you could pilot your vessel through the center of the ring, avoiding the infinitely dense edge. The forces would be immense, and the slightest deviation would mean instant destruction, but the path exists. In this perfect theoretical world, you have successfully navigated the most extreme object in the cosmos. You have passed through the looking glass. And what would you find on the other side? The idea of a shortcut through space-time is not new. It has its roots in the same theory that first predicted black holes, Einstein's general relativity. Back in 1935, Albert Einstein and his colleague Nathan Rosen were exploring the bizarre mathematics of black holes. They discovered something strange and wonderful hidden within the equations. They found a solution that described two black holes connected by a kind of tunnel or throat. This structure, which they theorized could link two distant points in space-time, became known as an Einstein-Rosen bridge. Today we have a much simpler and more evocative name for it, a wormhole. This was the first hint that space-time might have hidden passages. Imagine the fabric of space-time as a large sheet of paper. To get from one point on the paper to another, you would normally have to travel across the surface. This could be a very long journey. But what if you could bend the paper, bringing the 2 points close together? And what if you could then poke a hole through the paper, creating a direct tunnel between them?